So the title of my talk is Formal Methods for Complex Workflow Management in Industry 4.0. And before I start the presentation, I want to thank the organizers for this invitation and for giving me the opportunity to present to this community. And in fact, when I was preparing the presentation, I was a little bit worried because I did not know many of you and I was not sure where exactly you are positioned in terms of the research in this area. But after what I heard in the previous two talks, I think we are in business. So I hope that what I'm going to be presenting here will connect to what you heard earlier, okay? So let me try to make this connection a little bit more explicit by looking at some definition of Industry 4.0. And I just looked up this, word in Wikipedia. So from the article in Wikipedia, we see that some of the main goals in this paradigm are interconnection, which essentially means the ability to establish more effective and more efficient communication among the different components of the different production environments. The information transparency, which means the ability to process massive amounts of data and extract relevant information to use in the decision-making processes. Technical assistance, which means essentially the deployment of effective decision support for the different decision-making processes. And then there is this last bullet there, which is decentralized decisions. And this essentially means a quest for more extensive levels of automation and autonomy. And we heard already a lot about this concept, okay? So my talk is going to be focused primarily on this objective. And now, autonomy as an objective for manufacturing systems has a long history. Most of us here, from what I see, have been around for quite a while. And all of us will remember the concept of flex manufacturing system in the 80s and 90s. I'm not going to read the definition, all of us know what it means, but all of us also will remember that back in the middle of 90s, people tried to deploy fully autonomous flex manufacturing systems with the technologies and the methodologies of that era, and we had some big failures, right? So the message there was that if we want to really materialize this objective, we need a much more profound study of the workflow dynamics and the resource allocation function that takes place in this workflow. So now, since that time, there has been a lot of progress. We have much more extensive monitoring and communication capability, given all the deployment of manufacturing execution system, ERP platforms, more capable sensing technology, let's say, and communication technology. We have also much more robust and flexible automation, but this happens primarily, I think, from what we saw in the previous talk, also at the process level. I think we have been very good in deploying processing capability, but what I want to say, to report today, is progress that we have made when it comes to a more profound analytical understanding of the dynamics of the workflows that are materialized by these systems. And I mean real-time operations of these environments, right? So let me use an example here to explain where we see the needs. We have seen the needs and we have worked actually for a long time on this issue. And I'm going to use this very small manufacturing cell just to present some key issues, some key problems. So here you have this small robotized cell where you have three. Is this a pointer here? You have three. Anyhow, three CNC machines, R1, R2, and R3. It has a capacity to hold just one job at a time. The working tables are there. And because of flexibility, as we heard about flexibility as a requirement earlier, here we produce simultaneously two different types of jobs. Job type 1 goes from machine 1 to machine 2 to machine 3, job type 2 goes the other way. And traditionally, in the classical ORIE context, typically we want to control these workflows to maximize some time-based performance objective. Maximize throughput, minimize delays, this type of things. If you open an OR textbook, this is the typical requirement. But if you want to really automate the operation of such an environment, then here, this example demonstrates some additional problems that we need to address effectively. Here, remember again, job type, the blue jobs go from left to right, white jobs go from right to left. If we have loaded the system already as it's shown here, then no matter which job the robot picks to transfer to the next station, we're going to get stuck because the robot will pick the job, it will try to deposit to the next workstation, the workstation is full, we have a deadlock, the system basically gets stalled until somebody goes there to take care of the problem, we lose autonomy completely, right? So the point here is that if we want to deliver such autonomy, as we have been discussing it, we have been thinking for all this time, we need both to worry about efficiency, operational efficiency, as OR and IE, industrial engineering do, but we also need to worry about behavioral correctness, which is another important issue, right? And now, this issue of behavioral correctness, once we started talking about automated operations, is ubiquitous. Here, you see also the same type of problems arising in the operation of an AGV system. In this case, the resources allocated are not the buffers of the workstations, but are the zones that are used by the vehicles to go from one location to the other. If we do not do this allocation properly, again, we are getting stalled with similar type of problems. Now, the environment where this type of problems were first encountered and studied was the operating systems of the 60s and 70s that were developed for the big mainframes of the time. So let me just, I have a problem with my throat. So in those days, people realized that if they want to support the multi-threaded software that they were trying to develop for this type of computers, they need to develop operating systems that they would manage the resource allocation of this type of environments. And if we really want to deploy automation in the same way for manufacturing systems, we need operating systems for this, well-thought operating systems for this environment as well. And at least at a very basic level in terms of workflow management, a key function of these operating systems would be the deployment of such a control loop. The control, here we have a control loop where the plant is what we are calling here the RAS domain, and the controller is the big box at the top. The controller must monitor all the different events that take place in the plant, maintain some state representation of the system. From this state representation, it will get the feasible actions that can be commanded upon the system at any point in time. But not all these actions are good actions because they can lead to logical problems, as the deadlock problems. So from these feasible actions, you have to filter out the admissible actions, and eventually another part of the controller has to figure out which of these admissible actions to command on the system in order to optimize performance. And we need to support both of these functions, the filtering of the actions for logically correct behavior, and then the scheduling essentially function over the space of admissible actions. And for this, we need to provide representational and analytical capability to affect this control logic. And this is, I think, what we were suggesting at the very beginning of how we have to become scientific and formal and so on. And we have to develop models that will provide a seamless integration also of all these functions. And as I'm going to show later in the talk, another important issue once we go in this direction is to manage the complexity, both the analytical and the computational complexity that that underlies both of the type of problems that I'm pointing out here. So all these are important issues that one has to study systematically if we want to really develop a science for deploying such automated workflows. So from a methodological standpoint, the way we have tried to tackle this problem is by working at the intersection of these domains that I'm showing here: theoretical computer science, operations research, and control theory. And theoretical computer science provides all the representations and the analytical tools for modeling behavior and analyzing behavior. Operation systems, so with theoretical computer science primarily tackle the logical control problem. With operations research, we tackle the performance control problem, the scheduling problem, but also get all these tools that we need to define and address optimization problem at the design level or the control level. And then the control theory endows these other two domains with control theoretic concepts like state, feedback-based control, controllability, observability. All these are things that typically these people don't know when they stay within their territory. So we need to integrate all these perspectives on all these domains to deploy effectively solutions. And there is a community, especially in the controls society, that traditionally is known as discrete event systems, that has tried to work at this intersection. More recently, formal methods also have tried to relate to these problems. Temporal logic, stuff like that, yeah. People at UPenn, they have a big group there. Okay, so the main abstraction that we have used, at least in our studies, to tackle this, to model the operation of this type of environments for workflow management, is the sequential resource allocation system. And here we recognize the entities of this model is a set of resource types. Each type comes with a certain capacity because we have to respect the finiteness of the resources, right? And then this system supports a set of process types, like the types that we are discussing here. And each process type is essentially a set of processing stages. People in manufacturing realize this concept. And you need also a process plan, essentially some sort of sequential logic that relates these processing stages, right? And every processing stage, it needs also a set of resources to be executed. It might be the server of a given station, but it also might be buffering capacity, fixtures. All these aspects have to be modeled if you want to have autonomy, because you have to account all this resource allocation, okay? And we need also to understand the resource allocation protocol that manages, that affects these allocations. And once you go now to time-based performance, you need also to associate time distributions, distributions of processing times with all these processing stages, okay? So this is the basic model, the basic abstraction that we have here for our system. And we can further refine these abstractions based on the structure of the sequential logic and also the complexity of the resource allocation requirements. And you see here a number of possibilities. You can even bring in aspects like, as I said earlier, uncontrollable behavior, unobservable behavior, and so on. And all this is very important because it has allowed us to manage effectively the complexity of these systems, going from simpler models to more complex models. Now, let's look a little bit at the logical control problem. Here, a most straightforward way to address this problem is to model the behavior of such a system, of a resource allocation system, as a finite state automaton. So the state is defined by the number of active process instances at each processing stage. In this case, you have 6 processing stages, 3 for each job type. And the initial state is the empty state, where the system starts empty, and this is the goal state. You would like to be able to finish everything and get the system empty again. Now, the events that are typically recognized in such a resource allocation model is the loading of a new job type, a new job instance, the unloading of a job instance, and also the advancement of a job instance from one stage to the next processing stage. And if you start, essentially, when you develop what you call the state transition diagram of such an automaton, it's as if you are simulating the behavior of such a system. And then, in this case, for this example, you can deploy the whole state transition diagram, which is a map of all the possible behaviors that you can generate from such a system. And here you can see that you have white states for which you have paths back to the empty state, which means that you can finish everything without a problem. And then you have red states where unavoidably you end in some deadlocking situations. So your task as a controller, as a logical controller, is to keep the system in the white space, which is known as the safe subspace, and to avoid the unsafe subspace. You could do it in a twin, but here we're talking a more mathematical abstraction. How you implement it, it's up to you at the end, right? Yeah. I mean, you would have a twin running in the back, in the background, right? But yeah, right now I'm focusing more on the mathematical aspects, right? So from that standpoint, what you're really going to do is to be able to recognize transitions from the white region to the red region. And if you manage to do that effectively and block just those bad transitions that would take you to the red region, then you give the system the maximal behavioral latitude. Such a policy is known as maximally permissive. And in the context of this type of problems, it defines an optimal control problem, which is kind of different from the traditional optimal control problems where you worry about time. Here, you are still in the logical domain. But if you give the system, again, the ability to exploit all the white subspace, then when it comes to scheduling, you have the maximal behavioral latitude. So this is a good thing. The problem is that how would you do that? By every time you take a transition, you're asking, is this white, safe, or unsafe, red? The problem is that this decision problem is NP-hard. It's a difficult problem to decide from a computational standpoint. You can show formally using CS type of methodology that the problem is hard. And once you realize that, then you see also that this state space grows very large, very fast. These graphs for practical systems were going to grow very fast, very large, because the size of these graphs depends in a combinatorial way to the dimensions of the problem elements, of the structure that defines the problems. So here we have a complexity problem now, as I said earlier at the beginning of the talk, right? So how do I develop good solutions to this problem in the face of this type of complexity? And that's what we have done through the years. This goes back 20 years. And it's a community, not just me, who has worked on this type of problems. But here I'm going to be listing some developments that have addressed this problem. One first approach is to acknowledge the intractability of the optimal solution, the maximal permissive solution, and go for suboptimal solutions. In other words, what you want to do is to recognize more efficiently computationally subgraphs of the white subspace, which are strongly connected. So if you ensure the strong connectivity of the subgraphs that you recognize, that you accept, then you can always go back to the empty state. But you might be giving up some good states that you cannot recognize because of the compromise between computational efficiency and operational efficiency. So the very first policy of that nature is Banker's algorithm in the operating systems that I mentioned earlier, that goes all the way back to Dijkstra in 1965. But we have also results of our own of similar flavor. And we also have results, like with many other hard combinatorial problems in operations research, where we have identified special structure where the optimal policy becomes easily computable. You can have special structure in your system that if you exploit the structure, then you can get the optimal policy, the maximal permissive policy efficiently. We also have what I call here automated liveness verification tools. If you represent the systems in the PetriNet, for instance, modeling framework, then for certain types of policies, you can write down mathematical programming formulations that can tell you whether a tentative policy, deadlock avoidance policy from this class, is correct or not. will do the job or not. And the mathematical programming formulations involve a number of variables and constraints which are polynomially related to the size of the system. So it's easy to write them down. Of course, they are still mixed integer programming formulations, so they might be a little bit harder to solve, but it's traceable. Typically, it's tractable.
One sentence or two that for the students who are here and the professors, that it's okay to think about industrial problems and yet work in theory.
That's what I'm doing all my life. Since 1990, actually, just to give you a little bit of history, my PhD was Blas Ferreira, who's going to present later here. I started working with him in 1992. He gave me this type of problem, and since then, this type of research has been a major part of my research at Georgia Tech. And Georgia Tech is a good school that acknowledges this type of research.
There is a value to theoretical work, even if the end product is going to be industrial.
And actually, it's many things. If we want to leave this aside and start this discussion, I have a lot to tell you. But I'll tell you a couple of things. First of all, that, at least again, maybe you agree or not with me, but after 25 years, I realized, just from personal experience, but also observation from other people, that it takes a lot of time for this type of results to trickle to the industry. So there is a lag to go from the development of the theory to the full application of the theory. But we need to persist. We need to develop the theory properly before it is accepted. And then, exactly, you have formal verification. Even if your own work is not applied at the industry, it is archived. The archival value of this type of papers and results is also important. This is something that is not going to be surpassed. Some of these fundamental results are going to be there forever. It's not going to be that the next generation of technology will make them obsolete. Some of these classical results, theoretical results, are there forever. Now, since you opened this discussion, this type of research needs a little bit more support from NSF or other funding agencies also, you know, to keep us persistent on this task. So this is my, you know, bit of wisdom there. Okay, I'll give you a few more pointers. I'm going to wrap it up. What time? We have a little bit more time, right? We have some more time to. I don't know. It's up to you. Whatever you want. So some of the most recent developments in this area is the ability, and this relates to AI also, is the ability to develop and deploy this type of deadlock avoidance policy, especially the maximal permissive policy, as a classifier. So this relates to the data science type of methodologies. And I'm going to show you a little bit about this next. But before I go to the next slide, all these developments are documented here in a tutorial fashion, if you are interested to see what has happened in this area. This is a volume in the Now series on foundations and traces systems and control from 2017. So, I'm sorry. How we develop these policies as a classifier? The key idea here, we said it's a hard problem to develop these controllers, right? But the key idea here is to isolate the hard part offline. And once you have the policy, once you have this classification of all the state space to white and red, essentially you have a dichotomy. And then the question is how you encode this dichotomy in a classifier, like any other dichotomy that you would do in a neural net or any data science type of problem, right? You remember, the states are vectors of integers, essentially. So you have to take the set of integer vectors, which has been dichotomized, and find a way to represent which are the white, which are the red, which you know a priori, but now you want to encode this information in a way that you can process it efficiently. So what do you need? You need representations for the classifiers, and you can have parametric and non-parametric representations. If you go with parametric representations, you need to have guarantees that these representations that you chose can do the job, which is known as completeness. And once you have that, then you have also, within the space of the policies of the representations that you have chosen, to find representations that are parsimonious in terms of real-time execution, classification of any given state. We call this structural minimality. And at the end, you have to develop from the class that you chose this representation by parameterizing it appropriately. And in this task, you have to deal again with the explosive amount of data that you have from the state space that you mentioned earlier. And typically, you formulate this as an optimization problem. And I'm not going to go too much into these details, but just to give you a feeling of what would be a representation, a parametric representation for classification, it could be a set of inequalities. And so you have to define these inequalities so that if the state is good, white would satisfy the inequalities. If it is red, it should violate at least one of those inequalities. And in this case, structural minimality means that you want to have a classifier, such a set of inequalities, which has the smallest number of inequalities. And how do we design this? As a mixed integer program, or we can also relate this problem to the theory from OR of minimum set covering. And so you can do heuristics to get near optimal classifiers using results from minimum set covering. And all of this has been facilitated a lot by the fact that in our case, the notion of state safety is monotonic. If I have a state which is safe, any smaller component-wise state is safe. And if you have a state which is unsafe, any larger component-wise state will be unsafe. So this allows us, instead of dealing, when you do this design, with the entire set of safe states and the entire set of unsafe states, you can just focus on the maximal safe states and the minimal unsafe states. And this cuts down a lot the computational effort. So once you start looking systematically on these issues and you find the structure of your problem, you can gain a lot of leverage. Now, the thing is that linear classifiers are not complete because you can have such configurations of safe and unsafe states where you can have unsafe states within the convex hull of the safe state. So such set of states are not linearly separable. But again, using the properties of the state space, we can show that if you take now disjunctions of systems of linear inequalities, then you have a complete classifier. And you have extended the theory for this type of representations. All this has been developed, again, by systematic years of study of this type of problems. So what about the performance control problem? Here, to go from the logical control to performance control, essentially you have to augment your problems. You have to augment your models so that you can do the necessary computation and reasoning. So first of all, you need to trace more systematically the status of the processes at the different stages. Before, all you need to know is that you have a job in that particular stage. Now you want to know if the job has been started or is in processing or has been completed. So, but all this can be done by augmenting the automaton, the state space. Then you have to endow this automaton with timing information, and you could use deterministic timing in some cases. Exponential timing is easy from a computational standpoint because you have this Markovian property. But for any more general distribution, we know that you can approximate any such distribution to any degree of accuracy by a network of exponential stages. So we can still stay in this domain using phase-type distributions. All this is coming from the theory of operations research and stochastic operations research. You have to bring into this picture the deadlock avoidance policy that you have synthesized from the logical control part. And then you have also to express in the resulting semantics the performance objective of interest, maximizing throughput, minimizing delays, and so on. And another aspect that you need to take into consideration when you formulate and you deal with these performance control problems is whether you have stationary or non-stationary environment. Stationarity essentially in this case means repetitive manufacturing. You do the same thing again and again and again, and you might have randomness, but the structure of the distributions that define this randomness and the parameters of these distributions are invariant in time. So if you have that, and you bring in also into this picture the objective as an immediate reward function, you can formulate the problem as a Markov decision process. This is a very well-developed model in stochastic operations research. I will come to that. Here you assume that you have observability, yes. Yeah. I will come to that in a minute. Yes. But let me say also that non-stationary systems where you do not have some systematic repetition and so on, here randomness is more erratic if you want. So you have to deal with this issue in a rolling horizon scheme, some myopic control scheme where you look ahead first based on the data that you have, optimize myopically, and then you do it again in an iterative manner. And in control theory, this is known these days as model predictive control. It's a very hot topic. And basically, in classical control theory, when you do model predictive control approaches, you have to care about stability. So you have to make sure that the controller that you deploy through model predictive control is a stable controller. In our case, the notion of stability is the liveness. We want to make sure that even though we are myopic in our rolling horizon schemes, still, at the end, to get a live policy. And to have effectively deployed, at least in simulation, solutions of both of these approaches, okay? Now, for the Markov decision process, I'm not gonna, first of all, since you brought this up, we're thinking of situations like this reentrant line, where you have this manufacturing cell, jobs go first to workstation 1, workstation 2, back to workstation 1. So here you can have deadlocks because of recirculation of these reentrants, right? Now, if you have such a system, why you don't have observability? I mean, with all the sensing technology that you have available, why you cannot know where your jobs are or what is happening to them when they are at a given station? Why the observability assumption is a bad assumption here? Well, but I want to do it autonomous. The assumption is that, I mean, my objective is to deploy autonomy. That's what I'm trying to do. Sure, but
this is not the whole of planning, but not autonomous.
It's still a holy grail, I think. That we still would like in the future, further future, to see this kind. I don't know. Okay. Anyhow, so.
So maybe also you can learn is that we are not always after autonomy.
Exactly. Okay. At least here, the theory is developed aiming to how we support autonomous behavior.
Theory, everything works.
So in this case, anyhow, if we deploy the state space, then the key thing is that you have states where all jobs have been processing, and there's nothing to do there until to wait for a job to finish. This is an exponential race. But you have states where jobs are finished, and then you have to move to the next to advance some jobs. This is your decision. And the question is, how do you affect these decisions? How do you decide these decisions? And for this, you need to determine some decision logic. And this is the MVP, basically. But I was going to tell you, I thought when you asked me, you were going to ask me this question about the complexity again, because again, the state spaces can be all very large. But here is where we connect again with AI and approximate dynamic programming, reinforcement learning. You can do methodology like this to manage complexity here. You can do approximation in policy space. Choose some policies that you want. This solves your problem, the observability problem, because now you say, I'm going to define the policy in a way that it is doable in my environment, And then you have to parameterize the policy for optimization. And typically, you have to do some stochastic approximation method in real time or in simulation to figure out how to optimize within this particular policy space, which might consider the observability issue. And methodology which has been very efficient for us in our experiments is this idea of fluid relaxation. You relax the integral nature of the problem, and you fluidize the workflow. So define. Sorry. you fluidize the workflow. You formulate an optimization problem in this fluidized regime, which is much easier to solve, and then you try to translate the solution of this problem to a decision for your original problem. And this is very, very efficient. So I think I gave you the message that I was trying to give. So these are just the concluding remarks, that extensive levels of automation and autonomy, which are sought, at least I thought, for contemporary production systems, in Industry 4.0, necessitate the effective and efficient management of the complex resource allocation that takes place in these environments. And this resource allocation must be controlled both for operational efficiency and behavioral correctness. And currently, through discrete event system theory and formal methods, we have theoretical and analytical capability to support this type of analysis. And that's what it is said here. And so we believe that we have a good starting point, at least, for studying these problems. Before I close, I want to acknowledge the students who have worked on this set of problems with me, the funding agencies that have supported us, and this is a list of people who work in this area or have worked in this area, starting even from the people in the computer industry from the 60s and 70s. And these are the discrete event people, and also some manufacturing-related people who have looked in the directions that I'm suggesting here. All these are there. Thank you.